Uh, Thanks a lot. Yeah, that's exactly what I said. Thanks a lot for reminding me to record. And so, welcome all the people who are watching this from the recording sessions. We were talking about speech acts and Searle, who created sort of semi-formal definition of speech acts, and then Cohen and Perol actually created like a planning type of theory based on that, which was uh, which was very interesting because they took strips, the formalism for plans with preconditions and postconditions, and they applied it to speech acts. So that was the first formal system that had communication as actions and uh, applied planning principles on those actions. So the preconditions and postconditions are actually expressed in the form of beliefs and abilities and what and goals of agents, but we saw a nice example how you can actually formalize these, and then so these two things actually connected nicely together. So Searle is one of the important figures in computer science. You might have remembered him. Have you heard about the Turing test? Probably yes, right? Everybody did. Uh, so he is the author of the so-called Chinese room argument against the Turing test. Basically, he's saying that the computer, even able to communicate, is not really conscious or intelligent, and so on and so on. So that's his main one of the main things in theory of mind. The Daniel Dennett, another important person we're talking about quite often, countered his argument by actually several counter arguments. And so Daniel Dennett is saying, well, there's nothing magic about the intelligence. The intelligence is actually only like a complex system, and so that's an interesting relation that Searle has also influence on other parts of computer science. Still alive, now retired. He was active, but when I googled him last year, I saw that he had some troubles at Berkeley. He was at Berkeley, so he's now retired. Yeah, no comments on that. So from the planning theory, we're talking about 80s here. On speech acts, we actually have a development of agent communication languages, and you already are familiar with the FIPA ACL, right? ACL means Agent Communication Language, so there's nothing bright about the acronym. And FIPA is Foundation for Physical Agents. And so this FIPA ACL, you were using this one on seminars, is a natural evolution of earlier knowledge sharing effort by DARPA. That's a defense agency that is putting of United States, that's putting a lot of money into defense research. But as we've already seen, it is also the connected to the beginnings of autonomous vehicles. DARPA was organizing the so-called DARPA Challenge for autonomous vehicles in 2003, 4, 5, and so on. So in the 90s, the DARPA was having another call for research proposals about knowledge sharing, and out of these proposals, there came uh, two languages. One is called the KQML. That's knowledge query manipulation language, and another one is KIF, that's knowledge interchange format. So the KQML and KIF are two languages that are the beginnings of communication of multi-agent systems. And KQML actually matured into the ACL, the FIPA ACL as we know it now. Uh, and the KIF is still there. Uh, it's uh, it's still used, and it's basically like a first order logic formalism that can represent knowledge. We can use it for queries and so on. So the KIF is still there. The KQML has been superseded by ACL, which we are now using. So to put some order into our communication languages, if you think how the communication of agent works, it's sort of like sending letters. So basically, you have a message that contains all necessary information about who's talking to who and what the speaker actually wants from the hearer. That's like a speech act formalism. So what we're doing is that we're sending a message that looks like a letter with a post stamp here, and so it says from whom to who, uh, and then it says what you want to achieve. So the content of the message is actually a speech act. So for example, here you have all the necessities, and then you have the performative of the message, and that's defined by the agent communication language. So the agent communication language is sort of responsible for saying who's communicating to whom and what kind of speech act it is. And then uh, you have the uh, you have the content of the message, and the content of the message is usually expressed in this inner language, such as KIF, for example, or it can be, I mean, prologue, it can be whatever. So this content is like if we have a ACL message inform, so probably I inform you it's 12:32 now, right? So content will be probably something like time is 12:32. In order for the uh, all the parties to understand, we also have the third part, which we described earlier, and that's sort of the ontology thing. So we have a reference to the ontology usually described in all language, and the ontology is saying about the basic concepts we are using in the inner communication, right? So if the agent wants to be sure what the time means, the agent goes to the ontology description in order to understand. So these three parts are actually really important, and they have to work in accord to deliver all the messages. So we have the ACL part that's sending speech act messages with some information about uh, the sender, whom the message is, and a timestamp and things like that. It and then the content of the message. So this is a responsibility of the agent communication language up to the speech act, and the content of the message is described in some inner language, can be KIF, can be some other language, and the description of the content has to follow the ontology uh, that is described by in some higher level ontology language. So the ontology is responsible for specifying the dictionary we're using, specifying the hierarchies of the concepts, the roles, and everything. So the KIF, for example, has some formalisms to describe the variables, their values. The KIF is actually trying to be very powerful, although not really that readable, I would say. Uh, but you can express relations there. You have existential quantifier. Uh, you have universal quantifier, and so on. So that's for you to understand how these three things act together, and why we actually have three different levels of formalism. So you're familiar with ACL because you've used it, and you know that there are the informs and queries and requests, but also more complex things like subscribe to something, some kind of server sending information, confirmations, disconfirmations, and we will also see the call for proposal today, the CFP, that I think you also have been used at seminars. So the now let's move to some concrete examples of communication, and we will discuss communication protocols, and we will describe two most important communication protocols, and these are actually the way how we use task sharing, and so the protocols are well, they're connected to the CFP, but the protocol is called ContractNet or CNET, and you will recognize that it's actually the call for proposals from FIPA ACL. So that's one thing we will be discussing now, and another thing we will be discussing is the so-called Blackboard system. That's like an alternative way how agents can synchronize to do things together. So the Blackboard system, or BBS, is another approach. So these are two very important things we want to discuss today, and then maybe do some uh, other things like examples and cooperation of agents, basically some general notes. Next time we will be talking about interactions in terms of voting, and then auctions. So this is the program for the next two talks, definitely. And let's focus now on the communication protocols. So why should agent cooperate at all? Uh, well, of course, the idea is that we want agents in our multi-agent system to work together. But so far we were discussing, like half of the semester we were talking about agents are autonomous. They can have different goals. They're not hardwired, so they decide what to do at runtime, and so on. So to work together is not a thing that's for granted. It's not like when you actually create a system by hand, and all the components are created by you, and you don't have any autonomous parts of the program. You just call the procedures, and they work together. They cooperate without even knowing it. But the idea for agent is to be autonomous, intelligent, and so on and so on. So now when they are supposed to work together, it's sort of like counterintuitive thing, right? So So there has to be some protocols how agents can share information and share tasks. So sharing information we were talking about, it's part of the communication, right? When you're talking about how agents uh, cooperate in a multi-agent system, uh, you have the notion of coherence, how well the system performs as a whole, right? So you can have team of highly efficient agents, but if they do not cooperate well, then the overall coherence of the system is nothing special. So one of the first attempts to create a distributed problem-solving mechanism that was not connected to agents, but because it was in 80s, but it's called cooperative distributed problem solving. And that's one of the first attempts to actually, that's CDPS, and we're talking about 80s and Lesser and colleagues. And so that's one of the first attempts how to define what does it mean to for agents to cooperate on solving a problem. So this was a theory where the agents have some kind of capabilities, and they but the idea was that there was no competition and there was no autonomous behavior in terms that the agent can reject anything. So we when agents subscribe to a common goal, we call this benevolence, right? So we were talking about benevolent uh, agents, benevolence. So no conflicts, common goal, and focus on how to distribute the task, how to share a task. Uh, well, the benevolence is not really I mean, it's not be taken for sure, because benevolence means that an agent actually helps the whole system, contributes to the overall system performance, to the common goal, even if for the agent itself is disadvantageous, right? And this goes in contrast. So the benevolent behavior uh, means that the common goal is more important than your own goal. And uh, actually, the traditional way how to describe agents by maximizing their expected utility, right? So that's the way how we approached this before. So we want an agent to maximize its expected utility. So this is something different, right? So benevolence is in direct contrast with this, right? So the CDPS was actually really concerned with agents without their own goals and maximizing their individual expected utilities. So the benevolence was one of the key features, and this was actually a big simplification for the design. So it was much easier to define the protocols if you know that the agents are sort of slaves and you tell them do this and they say, yeah, yeah, I'm happy to do this. Uh, that simplifies the design. But the multi-agent system is actually a world that's much more complex, and the agents are supposed to be autonomous. We were designing them for years in this talk, for half a year almost, at least a couple of months, to be autonomous. And so they do not share a common goal. Still, we are concerned, why should they cooperate? How should they cooperate? How to identify and resolve conflicts? And so the cooperation is probably a matter of negotiation and bargaining. So it's not like, yes, yes sir, but it's more like what's there for me, why should I do it, from the point of an agent, right? So uh, the uh, the idea how we can share a task in CDPS is actually quite simple. We have some kind of problem description. So we have a problem, and we try to hierarchically divide it into subproblems, and then we define the subproblems. Uh, so we have a decomposition of the problem into subproblems, and it's hierarchical. So maybe we have another level of subproblems, and then we are assigning agents to to solve the subproblems, and then there is a mechanism responsible for uh, composing back, like synthesizing the sub solutions into a complete solution. But the idea is that the agents actually do it because they're benevolent, right? So the CDPS was focused on how to decompose the problem in general, uh, how to actually create an environment where the benevolent agents are solving the problems, how to synthesize the solution by sharing the results, and so basically when we identify the problem, so we have two things like sharing a task sharing. So when the agents are benevolent, this task sharing is sort of trivial, because the agents will agree to do if they know how to do. So that's why we have some kind of description, and each agent is checking if the agent is able to solve the problem, the task, and subtask. And then if yes, then the agent just solves the task, right? And then you have the mechanism for sharing the results. Uh, so it's also nothing special. You can think of basically two things how to do it. It's either reactive or proactive. So when we have the mechanism of this decomposition, as we see, so uh, we're decomposing the problem into subproblems. Do the task sharing, the agents happily agree to do it, and then when you have a reactive result sharing, then this guy who's responsible for this is actually waiting. So gets back one result, another, and that's pretty much it. So it's reactive behavior, waiting for all the three sub results to be submitted, and then doing something, right? Maybe sending the result to the higher level. Proactive is sort of, are you ready? What's the result? What's the result, right? So that's proactive. The reactive is usually enough in this case, because you sort of hope that the agents will fulfill. So that's the sort of trivial example how to do it when the agents agree to do it implicitly, right? Yes, you have to deal with how to distribute the task, how to collect the results, but that's more or less technical things. But the first real example of what we should call a multi-agent communication protocol is the contract net. And think of the call for proposals you already know from the seminars, because that's exactly that. The idea of the contract net protocol is actually quite old. It goes back to 77 by Smith and Davis. And the idea was that it tries to mimic the real life. So the contract net is actually trying to simulate a mechanism of contract. What does it mean to between humans or companies to actually agree on a contract, and how this whole mechanism work? So it's the mechanism of contract, and we are talking about task sharing, right? So the idea is to share a task sharing. So how does it work? Well, we know how call for proposals work, so let's just do the main steps. So the first is that you have a sort of a agent that's responsible for some task, and the agent cannot solve the problem on its own. So that's what it's called a recognition phase. Recognition, where the agent recognizes that it cannot solve the problem on its own. So you need help of other agents. Need help. The way how you get the help is by simulating the contract mechanism. So you're basically calling for proposals. That's why it's called ContractNet or CFP in agent languages. So what you're doing, you're announcing what's a call proposal. Hamza doesn't know what's a call proposal. Yeah. Okay. So I will describe it, but that's basically what we are just trying to describe. You have a problem, and you cannot solve the problem on your own. So you're sort of announcing the problem to your friends, right? Like trying to think of something you might need help with. Uh, Maybe you need a new shoes or something. So you're asking your friends, like, can you make me new shoes? So you're announcing between your friends, among your friends, and the friends, some of them can make shoes, some of them cannot. So they start the bidding phase. They're offering you some contract, basically. I can make you a shoes. They look like Converse. It will take 1 year, and it will cost 5,000 Czech crowns. That might be one of the proposals, right? So then you probably collect more proposals depending on actually how many of your friends can make shoes, and then you choose the best proposal according to your own criteria, and then you say, yeah, Yana, please make me the shoes, and then Yana starts making the shoes. Hopefully, delivers, right? So the recognition is the phase where you recognize, I need new shoes, and I'm not able to make my shoes myself. So you're doing the second phase, and it's called announcement. So you're announcing among your neighborhood, friends, contacts, that you need some task to be done for you. So, so here you have to specify the task, right? So you have to describe the task. Uh, Maybe some constraints. These can be like time, it can be money, and so on. And so the description has to be understandable. The constraints have to be part of the description. So you're announcing, I have this task to be done. And then the other agents, they start the bidding process. The bidding means that the agents actually receive your contract offer or call for proposal, and they decide if they want to participate, uh, if they are able to solve the task, what are their criteria, and maybe making you an offer, right? So the bidding phase is first decision: am I gonna make shoes for Hamza or not? And then you're submitting an offer. And the offer should contain some perimeters, uh, like if there is a deadline, so at least you should say you're satisfying the deadline, or you're telling how much time it will take for this particular agent to do the shoes. um, if there's a price, then offering the price for the shoes, and so on and so on. And then the you, as Hamza, who started the task, is now deciding which offer, which of those offers you are accepting. So you're deciding out of these tenders the agent submitted, which one you're selecting, and then you're awarding the job uh, to the agent. So you're basically selecting a winner among those bids, and awards a contract to one agent or more if applicable. So you're selecting a winner. And then the task is done uh, at some point. But basically, uh, what you see is that we are now concerned with the negotiation process, not much with how the task is actually done. We're sort of saying, yeah, and then the agent agreed to do it, so the agent will probably do it at some point, right? So that's a mechanism that's some kind of simple. It can be seen also as a formal protocol when we were talking about the FIPA ACL language. So the FIPA ACL have the CNET protocol, uh, and it's connected to the CFP uh, message, the call for proposal, right? So a for proposal is a synonym of implementation of a contract net protocol in some languages, such as the agent communication language by FIPA. And we can actually see that you have the initiator, and then you have the participants, and well, there can be more participants, right? Because it's sort of a broadcast, and and the and then this is sort of a timeline, and you can see what's going on uh, in different phases of the communication. So the initiator is actually sending the the call for proposals. That's like the first part of the contract net protocol, the announcement, right? So we're broadcasting the call for proposals to all possible participants, right? Usually there is some deadline to submit your uh, response. So uh, till this deadline, the agents can decide, deliberate if they're able to fulfill the job or not. That's described in the call for proposal. And by the deadline, they should say, like, if they are actually uh, agreeing to do it or not. So if not, so you're sending a refuse, according to the FIPA ACL protocol. So you're sending a message like refuse. Concerning your call for proposal, I refuse, right? And that's it. You don't do it. If yes, then you say sending a proposal. So you're sending a propose message. And the propose message should contain some perimeters, some details about your proposal, right? The shoes will look like whatever, camper, and they will cost 3,000 and it will take 1 month. So that's the proposal. You can also say not understood. That's sort of a general not understood message, just to inform the initiator that you did not understand. So uh, you can say not understood as well, but that's not the important one. So the important one is you refusing or you proposing, right? So the initiator now gathers all these proposals, and he's responding by uh, reject or accept messages. So the initiator is accepting some, and for this he's sending the accept proposal message. For some, he's sending the reject proposal message. Right? So the ones that are rejected are maybe not happy, they didn't get the job. Maybe they're happy, they're having free time for satisfying their own agenda. The one or ones who receive the accept message uh, starts working on this, and then in the end they're saying the message that the job has ended. And again, you have a couple of possibilities. Maybe the job does not have any answer. Maybe the job does not have any answer, so you're just saying inform done. Right? That's one possibility. If the task is actually resulting in some kind of answer that the initiator needs, so you're informing and sending the result. It's inform ref in ACL. So that's another possibility to sending inform ref. And another possibility can be that something bad happens, so you're sending a failure message, right? So that's the idea of a protocol, and you can see it as on a time scale, right? And you see those phases we were discussing before, that the initiator is distributing the task to participants. Then the participants have some time to react, and they're saying the proposal, and then some of them are getting the acceptance and then start working and then saying inform and then sending the inform with the result, right? So that's the idea. So see that this is really a task sharing. So you're offering a task, you're getting the responses, there's some like simple negotiation going on. Gabriela is commenting, this is like call for papers, except in that case, it's not you who are getting paid. Yes, exactly, not getting paid by money. When you have a paper accepted, it's a nice conference. You're getting paid by your own joy, and maybe eventually by some sort of scientific recognition. The rejects in this case are sort of harmful. When you got rejected, you're having bad thoughts and getting depression and so on. So not only there's no money for the acceptance, but there's a high stress factor for the rejection. Uh, doesn't sound like an advertisement for a PhD study, right, Gabriela? That's sort of dark humor here. Okay, so let's go back to ContractNet. It's really, really useful, really, really common, and it's one of the most commonly used protocols for communication. This metaphor for simple negotiation, uh, like a contract between companies or people, or a conference and authors, uh, it's really very useful, very simple, and it's one of the key protocols for agent communication. And what's really interesting is that for all the messages, not only for the call for proposals, but also for the informs and requests, we have a formal protocols that are described by this diagram, and the protocols are actually specifying who's sending what to whom in what time and in what situation. So with agent communication language, you don't only have the performatives like informs and requests and queries, but you also have simple protocols of the communication. And we have just seen the protocol for the call for proposals, which is one of the more complex ones. Although if you understand it, it's actually quite simple, and it mimics the uh, negotiation about the proposals and contracts in real life, right? So that's the FIPA-ACL. Again, I want to stress that this is an important part of multi-agent systems, and the ContractNet is very often used in practice. People were trying to come with some alternative, and so there are basically two ways how you can either improve the CFP, or you can try some different alternative. So one way how you can deal with the ContractNet or call for proposals is to create more elaborate mechanism for bidding, and we will be talking about more complex mechanisms for bidding. And this is in multi-agent system, it's called auctions. So we will be talking about auctions. It's called auctions also in real life when you're trying to buy something or even sell something on eBay. So you're actually participating in an auction. Uh, when you want to buy tulips in Holland, they have auctions for tulips. One of my favorite auctions was in Japan, in Tokyo, where they have daily early morning auctions for tunas, the fishes, the meat. And so we will be discussing auctions in detail, the different versions of auctions, and and it's actually a protocol that's more complex than a simple call for proposals. The bidding is sort of one round, but you can have auctions with more rounds, decreasing, increasing the price, and so on and so on. So we will be talking about auctions as one natural generalization of the simple ContractNet or call for proposals. Another way how to do it is to try something different, and the different thing how to share a task is the blackboard system, so BBS, blackboard system. So the blackboard system is a alternative protocol to ContractNet. It's different, and it's supposed to uh, do the same thing, to allow a platform for cooperation in problem solving. But the idea is more computer science-ish than with the CNET protocol. So we'll talk about the Blackboard system now, how it works. Well, the Blackboard system is actually the name suggests, uh, we are talking about some common structure that's accessible to all agent, and it's the Blackboard, right? Black. And it's the Blackboard. And the Blackboard is like a shared, uh, it's really like a Blackboard. And you can think that the idea is that you have many agents sitting around the Blackboard. Uh, so you have different agents here. They're sitting around the Blackboard, and they can actually read or they can write to the Blackboard. It's the so-called common structure for them, and they can access it. They read or write. This does not. They read or write the Blackboard, and the idea is that you share the task announcements on the Blackboard, and you also use it for sharing the results, right? So imagine that you start with some violet agent. The violet agent is here, and the violet agent is proposing a task. So he's sending a task proposal, but now instead of using the uh, ContractNet communication protocol, the agent is writing this to the Blackboard. Then what happens is that all the agents, these agents are sometimes called experts. So it's basically like some kind of seminar, right, of experts. So the seminars are sitting around the Blackboard. Somebody puts a task there, and so there's a task task description, and so all these agents, the experts, have access to the Blackboard. So they're looking at what's going on. Uh, this is asynchronous, so maybe there's the violet guy is actually putting another one, another task description there. So we now have two tasks to be solved, right? And so maybe one of the expert sees that it can solve the task, right? So maybe this guy is saying, yeah, I'm solving this task. So he's saying this task I'm taking, right? And then start solving the task, maybe in a trivial way. So for some time this task is being marked as being solved, and maybe for some time the guy is solving the task. Another guy is saying, okay, I will solve this task, taking this task to be solved. And then at one point one of the experts is probably who's solving the task, is saying, okay, and now I need like these two subtasks to be solved, and putting the subtasks here, right? This guy is really smart, or the green task was really simple. So after some time, the green guy is actually writing a result here. So we have a result already. But the violet task actually was divided into two subtasks, and then maybe some other guys are checking constantly. So we have two new tasks. Yeah, I can do this one, and working on this one, right? So what we're having, we have a Blackboard here that the problems, that the tasks to be solved are appearing here. The agents are observing the Blackboard, and when they see a task they can do, they're willing to do, they can take the task and solve it. When the solving the task includes definition of other tasks, so we can do the hierarchy of tasks here, and that's how it works. right? So we're slowly solving the tasks. The agents are working in asynchronous way, and uh, the task can be defined on different abstraction levels. So you can have experts understanding only some of the tasks and so on, right? The idea is that it's sort of this blackboard system. Everybody can read, everybody can write, and the agents are subscribing, maybe defining other uh, tasks. Yeah, Robert is saying that uh, multi-threading tasks just a bit more chaotic. Yeah, yes. The the way how I describe it, it's the general principle, and it is some kind of multi-threading thing. So you see, from the it depends how you actually technically realizes it, but you can see that the blackboard is actually also some kind of bottleneck, right? They all have to have access there. They all can read and write. So the blackboard on one hand is sort of a bottleneck, but you expect that solving the tasks actually takes much reasonable time and effort than communicating about the tasks. So the idea is that you hope that the communication is not the time critical thing, right? So the experts will not access the blackboard every thousandth of a second or something, right? It's like with real experts and real blackboard. They can be around the blackboard, but at one time there's only one expert who's reading or writing something, and then the experts actually thinking and solving the tasks, right? And another thing is that the chaos that you can see, it can be actually much more organized because we have ontological description of the tasks, right? Ontology is pink and very bold, pink. So for each task, we have some ontological descriptions. So even if the messages about the tasks are sort of appearing in asynchronous way, the agents, they also have their ontological descriptions of what they can do. So they're only reacting only on parts that falls within their rank, right? The capabilities. So by ontologies and description of the task, we can actually put more organization into the Blackboard system, right? So typically, you can have messages on different abstraction levels. And so the Blackboard system can be structured, and some experts understand the dark pink, some understand the light pink, and so on. So you can have hierarchies there in the messages, and so the agents actually can be a bit organized. But the idea is, yeah, like any kind of distributed computer system that accesses a shared resource like a memory, basically. So uh, what we uh, what we have that to summarize more in a sort of more programming way, we have the blackboard. I will be writing. We have the blackboard that's like a shared memory, but we have to make it more organized. So Robert is more satisfied. It's not total chaos. So we have some formalism how to describe task. Uh, Usually, you have some kind of um, hierarchical order of the tasks. Uh, so in order to be practically usable, the blackboard should be organized. and the description should be simple, but using ontologies and so on. Then we have the experts. These are the agents, right? The experts are the agents, problem solving agents, uh, and they need to understand at least some of the messages and execute actions when they are selected, right? So there's nothing special about the agents. They're just called experts here. We also need some kind of arbiter mechanism, the some kind of organizer who's uh, who's responsible for running the Blackboard system. So selecting the agents, selecting the tasks that are coming, and so on and so on. And the arbiter can actually be something really simple, but it can also be a thing that sort of seeks for some motivation of the agents, like the higher level program solving capabilities. But the original idea that you have a bunch of agents with common access to the blackboard, and they sort of understand what's going on the blackboard, they can get the task, solve it, and write the result back, maybe writing some other tasks in the meantime during the solving, that's still there. And you can see that it's very different from the ContractNet, but on the other hand, it sort of serves the same purpose, right? We are sharing, redistributing the tasks. So it's interesting that this Blackboard architecture is actually very popular in games. There's a chapter in one of the Bibles of game programming, AI, game programming wisdom book. There's a whole chapter on Blackboard architectures. So programming some kind of artificial intelligence for games is one of the cool applications of the Blackboard system. There are actually even multi-agent systems, like practical implementation of multi-agent system environments that are uh, totally based on the Blackboard system. So the whole communication actually takes place in the Blackboard. So it's not only about task sharing, but it's about any kind of communication. So imagine that you have a system, a multi-agent system, where the agents communicate only through the Blackboard, right? So imagine you have a Blackboard and you're actually writing your message, uh, and it's like from agent Roman to agent Anna. The content would be, I don't know, make me a coffee. And so this is agent Roman, and here we have other agents, like Anna, Yana, Donna, Ivana, and so on. And so you're sending a message from Roman to Anna, make me a coffee. And which one is Anna? This one. This is agent Anna. The agent reads that it's to her, and the content is make me a coffee. So the agent receives the message by reading a Blackboard uh, and putting some response there, like saying no. So there are some systems where the whole communication of agents is not done by messages as you saw it in FIPA ACL uh, or environments, but it can be, the whole communication can be done through the Blackboard system. So it's not, I mean, some crazy thing, even though we understand that the Blackboard itself can be a bottleneck, but if there's not so much communication, it's still a nice, sort of a simple way how to do it. Mm, an example from the game is actually one of the gay AI based games, and it's even called BB War. Like that's the game where it's like a simulation of army battles, and the idea how to do the artificial intelligence part of the game, the control, is that you actually have the blackboard where you put tasks, and then the experts, the agents, are uh, capable of solve different tasks on different hierarchies. So it's a military, right? So they have a strong hierarchy. So the so maybe you have a general, and the general understands tasks like attack city, right? So if there is a task, attack Brno, for example, the general takes the tasks because he is capable of attacking city on this level. And by solving this task, attack Brno, he's actually thinking of how to do it, how to solve the task to attack Brno. Well, and so he's creating a list of tasks how to attack Brno. So he's saying, okay, first we attack Svobodák. That's one of the squares there. Then we attack the city hall. We should attack an airport. I'm not sure if they have airport in Brno, but there should be some airport. At least in Vienna, there's an airport. So the general is taking the task of attack Brno and putting tasks: attack a square, attack a city hall, attack an airport, right? And then you have different experts around here that can understand this. So, for example, to attack a square, the Svobodák, you actually, what you need is maybe a tank, right? So, an agent tank understands attack square. So, an agent tanks are, I don't know, dark gray. The tank says, yeah, I'll take the task, attack the square, right? Consider it done, sir. And to attack a city hall, you probably need a troop of soldiers, right? So you have the troopers, because you need real soldiers to come to the city hall and kill the mayor, right? So the troopers are attacking buildings. So yes, we're attack the city hall. And to attack an airport, you probably need a jet plane, right? So the military jet is taking the airport. And so the general is operating on one level, and the attack city uh, task is divided into three tasks: attack different locations, and for different locations, you have different agents attacking the different locations because they are specialized on it. You have one the troopers, you have the tanks, airplanes, and so on and so on, right? So this is how you organize the blackboard in a hierarchical way, and probably the tank can have a hierarchy of its own goals, sub goals, maybe needing help. Sometimes I don't know, the troopers need help from the tank or from the jet, so they can create new tasks, putting them there. But you understand that the blackboard can be actually quite organized in a hierarchical way, and so uh, it can be actually a very useful way how to share tasks and results. Right. Okay, so to conclude, the Blackboard system is a very simple mechanism for agent coordination. It serves for task sharing and sharing the results of the task. And the pros are that it's sort of simple. Uh, you do not expect the agents to know much about other agents, and they still can work on their tasks, creating new tasks, and so the ontology for the task description doesn't have to be very um, complex. The messages typically are written and rewritten, maybe creating new tasks, subtasks, and the idea usually is that you have more monolithic systems where the agents share the same architecture, but it's not necessary. And as I've said, some some multi-agent systems are used have are using the Blackboard architecture to exchange general messages, not just task sharing. The Blackboard itself can be a bottleneck if there's lots of communication, but in general, you expect that the communication is not that dense. You're not communicating that much uh, relatively to that you're actually processing your agenda, doing some tasks. Right. So the Blackboard system is one of the very useful, common used environments, algorithms for task sharing. The contract net is sort of more traditional, ordered way how you distribute the tasks, but the Blackboard system is also quite cool. Okay, so that's that's actually the main part of this talk, and you should take care to understand the contract net and the Blackboard system, because they are really useful, and it's one of the good outcomes from the multi-agent systems uh, area. So one of the I will be talking about the results sharing a bit more, but only briefly, showing one example, and then we'll sort of trying to make our introduction into interactions of selfish agents or self-interested agents. Uh, so the one of the examples for the results sharing so far, the results sharing. So for the task sharing, we have these mechanisms like contract net. So yeah, let me make it more organized. So for task sharing, we have the contract net, we have the BBS. We can have some auctions, but auctions can be used for other things as well. We will see. But for the results sharing, it's sort of how to share results, right? You share a task, so the sharing of result is sort of a general consequence of this. You share a task, the task ends, and you send the result to whoever started the task, ask you to do the task, and that's pretty much it. But uh, so it's really straightforward, right? Even the BBS is saying, okay, I have the task here. Somebody takes care of a task and writes a result, and that's it, right? We have the result there. Uh, for sharing a result in practical applications, usually it's that trivial, but sometimes you have to solve cases how uh, how reliable the results are. So in some critical applications in practice, you should consider things like confidence, because you're delegating in the call for proposal, you're delegating the problem to one agent. Then the agent uh, comes with a solution, and that's pretty much it, right? So uh, you sort of rely on the agent. So one of the ways how to get more confidence in results sharing, so maybe you tell more independent agents to solve the task and then compare the results, right? uh, Sometimes the completeness is an issue. So each agent, we know that each agent is sharing a sort of local view on the problem. So maybe solving a problem from its own perspective. I mean, if it's a shoes, it it's shoes, right? But you can have a problem of searching for some information. So each of the agent can tell you, yeah, I can find you the information, but each of the agents can find you only part of the information, and maybe to get the more complete point of view, you again need more agents to actually fulfill the task for you. Another thing of the why to share the results, or why to employ more agents to do the same task, uh, is the precision thing again. So for some tasks, uh, you need to be sure that your solution is precise. So for example, I don't know, imagine your agents are actually deep neural networks. So you're solving a task, maybe asking more different architectures of neural networks to solve your task, and then creating an ensemble from their answers. So this would be a nice example of sharing results in a sort of clever way, right? So, so this is about results sharing. That sometimes you're happy with one agent fulfilling your job. Sometimes, if you want more confident, complete, or precise answers, you should probably be employing more agents and think uh, how to synthesize their answers into one more complete answer. So, another interesting example from the medieval ages of multi-agent systems, that's from the Wooldridge book, Michael Wooldridge on multi-agent systems, is the Fairlean system, and it's from 1990. So there was not much known about agents, and it's really before KQML or ACL. And so Wooldridge is probably using this example because it's his own work. Uh, but the idea is that the feline is actually a distributed expert system. And the expert system, you can think of it as a sort of prologue program with some database of knowledge, and you can query the database about the knowledge, right? The expert systems in the early 90s, they basically vanished because there were some problems in actually designing them, because the expert system was supposed to be like logical formulas modeled with the help of a human expert. And so they do not scale well, they do not work with imprecise information, although they can, through the reasoning mechanism, they tell you how they found out the result, because they show you the derivation of the result. On the other hand, they did not tell you anything about the like confidence of the result. So Woodrich and Jennings were trying to do the distributed expert system, where the knowledge is distributed, and they had subtasks, and they distributed the task. So they define sort of agents, and each agent was a expert system or a rule-based system. And for each agent, they had to define the skills, what I can do, and the interests, what I need, what I'm interested in knowing. So the skills and interests, I need to know. And that was their idea of a distributed expert system. So they had agents with partial knowledge, and they could describe in a sort of ontological way uh, what they know, and then they could describe what they want to know. And then there was a communication part where you had the sort of arbiter, the server here, who was trying to organize their jobs, receiving some tasks, and then con- communicating with the experts, comparing what they know, what they want to know, and gathering the information and distributing the information. So this is like one concrete example from the times where the agents were only being slowly born, but you can see that the distribution of actions is actually uh, an important issue, and gathering the results. So we've seen a couple mechanisms how to do it. And the last thing, what I want to say today is just a short introduction into the next lecture, uh, where uh, when you are talking about the interaction of agents, we were discussing the benevolence, right? The benevolent agents, they're doing whatever to join the common team and to fulfill the common goal. But in general, this is very ideal case, and we don't want it, right? So when you are talking about general interaction of agents, you can think of that agents can actually help each other, but they can really like obstruct, uh, uh, which can be like even a physical obstructions, like when you're thinking of robots, swarms of robots, uh, then this can really mean like obstructing. The agents affect the environment. Uh, so we will be studying different types of interactions about the agents in multi-agent system in general. And how to actually do it is to start with the most simple case. And so we will start with a very simple case, interaction of two agents, and interaction of agents that are not benevolent, but they are selfish. And this is where the game theory comes into play, because it is the game theory, the basics of game theory are actually interested on agents that are so-called rational, which means they are selfish, right? They are maximizing their own expected utility. And the simplest case that's been described in the game theory is that you have two uh, those rational, read selfish agents that are trying to compete with each other, because you have some kind of game, right? And the utility, it's usually it's like a zero sum game. So if one agent wins, maximizes its utility to some nice sum, then the other agent loses, right? So this is what we will be doing next week, trying to see the basics of game theory, how it applies to artificial intelligence, and the strategic thinking, how to maximize the utility, and how you can actually create a system that achieves some kind of common goal in an efficient way, even with those sort of rational or selfish agents. So this is the program for next week, and we will see some examples of the game theory, the voting strategies, and then finally auctions. And but I think it's a program for 2 lectures, so we will see. It's I hope it's interesting. So today it was more about practical things, and don't ever forget the two important algorithms, and I will write them in red. So it's the CNET, really important, and the Blackboard system, really important and kind of cool. So thanks a lot. Thanks a lot for your attention. And see you next week. See you next week. Bye bye. It was a pleasure. Bye bye.